So, good evening, everyone. We'll start today's session. Then let me share my screen. So, is my screen is visible?
Yes, ma'am.
Yeah. Thank you. So, yesterday we have seen the introduction to GPU and how the controls are, how the data is flow between GPU and CPU, everything, and some small program about how to execute CUDA program on Colab. So in today's, we are seeing GPU programming and Hello World. Here, my agenda is what is parallel computing, heterogeneous architecture, CUDA, a platform for heterogeneous computing, Hello World from GPU, and CUDA C program structure. After that, we can see some programs, those programs are executed using CUDA. So, while considering parallel computing, there are two distinct areas of computing technologies are available. One is computer architecture in the hardware aspect. Another one is parallel computing in software aspect. So here, either you can do programming using software for parallel computation. So otherwise, and somehow in GPU itself used for parallelization. So in sequential programming, the problem is divided into small pieces of calculations, and each and every pieces are in some way of having some dependency. So one task is executed at a time. After that, the next one is executed. After that, the next one. It goes on like that. In parallel execution, if there is no dependency, one or more tasks are executed in parallel way, and somehow somewhere some sequential execution may be there. And there are two types of parallelisms are available. One is task parallelism, another one is data parallelism. In task parallelism, so what we are doing is we are dividing the task into smaller pieces, and um, that may be independent task. Then we can easily parallelize all the tasks, so across the multiple cores or multiple processes. In data parallelism, there are many data items are there. So all the data items can be operated on the same times. And this data parallelism mainly focusing on the data is shared among, or data is given to multiple cores at the same time. So here, CUDA programming comes into picture, and it is well suited to address the problems that can be expressed for data parallel computations. Mainly, CUDA programming is mainly used for data parallelism. So we all know that this in heterogeneous architecture, the CUDA programming is mainly for heterogeneous architecture. So here we need both CPU and GPU. That's why we are saying that it's needed some heterogeneous. And already in yesterday itself, I told there are two parts are there in heterogeneous applications. One is host code, another one is device code. The host code in the sense the code which is executed in CPU, and the device code is the code which is executed in GPU. And host code runs on CPU and device code runs on GPU. The host means CPU and the device means GPU. Okay, so in GPU, there are two important features are there. to describe the capability of GPUs. So one is the number of CUDA cores, another one is the memory size. So there are two architectures have given here. One is Tesla C2050 and another one is Tesla K40. The Tesla C2050 is Fermi series and K10 is Kepler series. So the number of cores in this one is first one is 448 and Tesla K10 it is having 2 into 1536. There is a huge variations in number of cores. In Fermi, the memory is 6 GB and Kepler Tesla K10 the memory is 8 GB. The peak performance is for Tesla C2050 it is 1.03 teraflops and in K10 it is 4.58 that is teraflops. That means terafloating point operations per second. And the memory bandwidth is also increased, double the memory bandwidth, more than double the memory bandwidth in K10. So here, this architecture describes the platform for heterogeneous computing, that is CUDA. So there are n number of libraries are available in CUDA. So you can use those libraries for executing different applications. In the bottommost layer, there's having C, C++, Fortran, Python, direct compute and directives, that is OpenACC compilers are available. So you can use any one of these programming languages for writing CUDA programs. And above that, we are having a number of libraries. So you can use these libraries for executing different applications. So above that, we can build any CUDA computing applications. So in last class itself, I told the CUDA C is an extension of ANSI C and uh, which enables that extensions enables for heterogeneous programming. So we can also say CUDA is a API. So it also manages devices, memory, and other tasks. And there are two API levels are available in CUDA. One is CUDA driver API, another one is CUDA runtime API. So it's shown in the diagram also. So in the CUDA driver API, it is a low level API and it is very hard to program, but it provides more control over how GPU devices is used. So all the driver support is given by the CUDA driver API. And the next one is runtime API. It is a high level API. So it is implemented on top of driver API. So above that, you are having the CUDA libraries. So in top of all those things, we can develop applications. So in the bottom layer is our GPU. So the CUDA driver and CUDA runtime API and CUDA libraries, everything we can install on CPU. Then only you can your CPU can able to identify GPU. So and it can automatically transfer data to GPU and it can retrieve the final results from the GPU. So this is a very important one. It shows the CUDA C program structure. And here, the main thing is NVIDIA CC compiler, NVIDIA C compiler. And what the NVIDIA C compiler will do is it splits the CUDA program into device code and host code. Host is in the sense CPU, device is the GPU. Okay. So both these splitting is done automatically by the NVCC compiler. And so then what happens in the actual ANSI program happens here itself. Then the pre-processing, compiler, linker, compiler linking, everything happens in the host part of the code. And in the device part, it acts as a just-in-time compiler. So uh, both the part are important for accessing for GPUs for its computation. Okay, so this is the main thing. You have to remember what happens while using NVCC compiler. So the CUDA program is splitted into host code and device code. Then host part is executed in CPU and device part is executed in GPU. And all the data transfer between CPU to GPU and GPU to CPU, everything is handled by the CPU. Okay, so while executing any programs, so what you have to do is we have to check whether the compiler is properly installed everything. So already in the last class itself, we have discussed everything. Then I'll give you a recap. So first one is, can you able to see my screen? The Google, the Colab is able to see. Someone can message. Okay, okay. Thank you. So if you are attending the class using computer, so or any laptop, you can open the Colab and you change the runtime to uh, some GPU and save it. So use this particular command and you will see the CUDA is installed there. So and where it is installed, you can check. So all the commands you can use Linux too. So it will shows and you can see the version there and how many GPUs are connected. You can see using this particular command. So here in runtime, so we are having only one GPU and it shows NVIDIA 0. Okay, so it means there is only one GPU. So the properties of that particular GPU can be seen by with the help of this particular command NVIDIA-SMA. Okay, so I'll move on to here. So to write any CUDA C program, so you need a source file. So with the extension of .cu, and you have to compile that file using NVIDIA NVCC compiler, that is NVIDIA C compiler. So you can execute the file using command line. So where the kernel code executed there in the GPU. So already in the last class, we have executed this Hello World program. So it's a simple C program. So all the C program you can execute using NVCC compiler. The main condition is you have to be stored that program in .cu extension. Then only we can able to execute. The execution command, you please note down. Anybody is joined today newly. NVCC, the file name for output, you give some name, file name. So you executed, you will get the hello world from GPU. So what was printed here, that will be shown here. So in last class itself, we have seen this particular program. Okay, so I have executed this program here. So while executing CUDA programs in Colab, you have to remember to give double percentage, then give write file, then file name. Okay, so after that, you simply execute, run this cell. So the file will be written onto file first c.cu, that is the file name I have given. Then you run the program, compile the program. Okay, it's compiled. Then run using this statement. Okay. Okay, this is another program. So it's again used for printing the hello world. So this is a empty kernel. So already I told you there are two parts in CUDA C program. One is called um, GPU part, another one is CPU part. So our host part or device part. So here this particular global void kernel. So this is a function which is mainly executed there in the GPU. Here I have written this function as what empty function. So then the C main function. There I have called this particular function. This name may be any name. Already I told. I'm repeating today. So kernel 1 comma 1. So you print. There is one state print of statements. Hello. So CUDA device reset. So this one is mainly used for resetting our GPU. Okay. So that's all. It's simply print hello because there is nothing is executed there in the GPU. Okay. So here the CUDA program structure is having five main steps. First step is allocate GPU memories. Whatever data you want to process, for that you have to allocate GPU memory. Copy data from, of course, we have to allocate CPU memory too. So copy the data from CPU memory to GPU memory. And if somebody is joining late, I have to give some admit. Sorry for that. And invoke the CUDA kernel to perform program specific computation. That is, I'll show. So invoking kernel means writing this particular statement using angular brackets. And copy data back from GPU memory to CPU memory. So once everything is copied from GPU, you can free the GPU memories. Okay, so here I have specified everything. And see this program, you know what is inside the main arguments. So command line arguments you can give. So number of command line arguments that is specified in ARGC. So here in this kernel program, we have printed one statement GPU hello. And the kernel launch says hello triple angle brackets 1 comma 10. So the main part of this particular statement is called as kernel launch. And here the structure is the kernel function name, triple angle brackets open triple angle brackets. This is block number. This is a thread number. I'll explain later. And here I am using only one block and 10 threads. Okay, in the last class itself, I told there are n number of threads are available in GPU based on the number of cores available. So you can use any number of threads and any number of blocks. We'll see the block and thread concepts later. And this particular statement is called kernel launch. Okay, again, I have used the CUDA device reset. So already this particular program is executed. So I'll show this. So see, this is a program. And here, before global, there are two double underscores are available. After that, also there are two double underscores are there. Okay, this is a standard format. So global void, hello void. So there is one printf statement is there. So again in CPU part, there is one printf statement. Already I have executed this particular program. So the CPU hello will be executed first. After that only I have launched the kernel. Then there are, I called 10 threads. Okay. So this will be executed 10 times. GPU hello will be executed 10 times. Same code will be executed 10 times. So anybody want to execute this particular program? Please copy from the chat. And for executing, it's very simple statement only. Yesterday I have included some flags. I have removed all the flags. There is no need of using flags. This is an executing statement. The file name alone changed for different programs. Simply note down how to execute. Okay. So already we told there are two set of codes are available. One set is called kernel program or device code. Another is CPU or host code. Okay. This part is called as the first part is called as device code. Uh, this is a CUDA keyword global, which indicates that the function runs on the device. So we are going to execute what are the calculations or what are the statements given inside that function in the device. That means the GPU. So it should be called from the host code, that is CPU code. Okay. So already I have explained this one. This NVCC plus source file into host and device components. So all the this NVCC compiler handles device function like kernel, and the host compiler handles host function like main. Okay. So the kernel function is handled by NVCC compiler, and the host compiler handles the main function. Okay. So the next statement I am going to introduce is CUDA device synchronize. Okay. Okay. That's the same program. So instead of giving CUDA device reset, so the CUDA device reset is another one, and CUDA device synchronize function is another one. Because why we are using CUDA device synchronize is, and the CPU function and GPU kernel both run asynchronously. Okay, to synchronize both GPU and CPU, we have to use CUDA device synchronize. Okay, so I'll paste this code. Then okay, so already I have executed this one, I think so. Yeah, it's here. So here in this particular program, I have given only one single hello world statement in kernel program. So only one block, only one thread. So only one time this function is executed. So I'll be getting hello world. Okay. So there is no difference between here in this particular program. There is no difference between while using CUDA device reset and CUDA device synchronize. Okay. So what the CUDA device reset will do is um, so what it will do is it makes the host, that means the CPU, wait until the device, that GPU, have finished executing all the threads you have started. What are the threads you have started there in the GPU? That all executed. After that, only the what are the things you have to be executed and the CPU will be executed. Okay, that will be done with the help of CUDA device synchronize. So we'll see some example. Through that example, you can able to remember, able to identify what happens while using um, CUDA device synchronize. This is another one program. So here, three times the kernel is launched. Okay. So after that, CUDA device synchronize is called. Then there is one statement, printf statement on CPU. Okay. So can you guess the output for this one? See here what happens is we are using CUDA device synchronize. What happens? So what are the statements or what are the threads invoked there in the kernel will be executed. That is, GPU will be executed. After that, only the things which are to be executed in the CPU will be executed. To do one thing, I have pasted the program here. So you execute that program. I'll wait some time. You execute the program. So initially you give CUDA device synchronize. The next is you remove CUDA device synchronize, then execute. Then see what happens. So after that, you paste the CUDA device synchronize after printf statement in the CPU code. Then you execute. Execute all those things and type the message here in the chat. So see here, what happens here is I have launched a kernel here, 1, comma 1. So hello world is printed. I'll launch the kernel here. Again, hello world is printed. So after that, one more time, the hello world is printed. So after that only, then I remove this one. I'm saving that program. See here. So what is the output on CPU? So I didn't given the CUDA device control. Directly it goes to CPU and it does printer. What is there to execute there in the CPU? Minute, 1 minute. Again, I am saving the program, compiling it. See here. So the CPU won't wait. Okay. So whatever things there in the CPU that will be executed. After that, the both CPU and GPU are synchronized. Then the kernel program is executed. Okay. So there's a functionality of this particular CUDA device synchronize. Okay. I'll move on to the next. Say anyone is executing? Am I audible? Okay, okay, thank you. So the next program, we'll see the next one. Okay, here there are two kernel programs are there. So the first kernel program is launched here and the second one is launched here. So then CUDA device synchronize, after that printf on CPU. Okay, so we'll execute this one. Okay, so already this program is there. Okay, so we can give any number of kernel programs, it's not a problem. Okay, so it is having CUDA device synchronize. So the first kernel is launched first and the second kernel is launched second. So after that, uh, what are the things there in the CPU will be executed. Okay, this is the thing. You can change. Then execute, compile. Okay, see here, and so initially this will be synchronized, and that is executed. Okay, so after that, that is skipped. Then that is the CPU part is executed. Okay, so you have to carefully give CUDA device synchronize, then only the data will be executed correctly in GPU. Otherwise, we won't get the correct results. Okay. So can you execute this one and or predict the output there in the chat box? I'll simply paste this to chat. So all the PPTs and the video materials have been shared using the Google Sheet. So already you people have received some sheet. The sheet itself, all the programs and videos, everything will be available. Okay, anyone? Anyone can predict the output here? Or anyone executed the program? You can paste the results. Nobody has done. Okay. Next is I have to compile. Sorry. So while pasting, what happens is some error. You can see here the results. So initially, the CUDA device synchronize is here. So what happens? The CPU codes are all the CPU codes are executed. So uh, after that only the kernel is called one by one. Then the statement, the printf statement after the CUDA device synchronize is executed. So I think now it is clear. And if you want to execute something on the GPU first, and GPU has to be called first, what you have to do is, so what are the things, what are the kernels or how many kernels you have written, all the kernels has to be called or launched. After that, you write the CUDA device synchronize. So then you write what are the things you have to be done with the help of CPU. Okay. So otherwise, what happens is the things which are the statements which are needs to be executed in CPU will be executed. Then once the CUDA device synchronous is identified, then all the kernels are launched. Then the sequences goes on like this. Okay. So now you could understood what is the use of CUDA device synchronize. And already I told, okay. So the host wait until the device has finished executing all the threads you have started. Okay. So next is hello world in parallel. So CUDA and GPU both are very much used for massively parallelism. Okay. So in the previous program and all, we are not having any parallelisms. Okay. So here, what we have, I have done is in the kernel, it is having one printf statements. So how many threads are having is 32 threads. So the 32 threads are executing the same kernel. Then what happens is we'll be getting, okay, if you want, I'll change to 32. Then I'll call this the GPU 32 times it is executed. Okay, so we are here in this program, we are not writing any parallel code. Okay, simply giving how many blocks, how many threads, that's all. Okay, all the parallelization happens in the backend with the help of CUDA. Okay, so that's the beauty of this CUDA program. Okay, so otherwise it is very difficult to write parallel codes. Okay. So till now, we have seen some of the Hello World programs, how to execute with the help of CUDA device reset, CUDA device synchronize. Okay, all those things. Okay, so next one is symbol calculation. Okay, we are adding two numbers here, two integers here. So already I told you. So for storing any values, you have to allocate memory both in CPU and GPU. Okay. So all have done there in the CPU part of the program. That is host part of the program. Okay. So here the first part, the function which is there that declared in globally, that is called kernel. And in the C program, I have declared two variables. One is C, another one is pointer DC. Okay. So once you, this is for the C is for storing variable in CPU, and pointer DC is for storing there in GPU. Okay. So if you want to store any data onto GPU, what you have to do is you have to allocate memory. Okay. So like C program, we are having some memory allocation statements like. So here we are having one statement called CUDA MLR, CUDA MLR. Okay. So here the syntax is we are having void double star ampersand of DC. DC is the variable which is used for storing data in GPU. And how many size amount of memory allocated is size of int, because we are storing one integer variable there in GPU. Okay. So the kernel program says we are adding two numbers, integer A and integer B, and the result is the integer C will be stored. Okay, star C equal to A plus B, that is the statement I have used here. Okay, sorry. And what happens here is either what you can do is either you can use scanf statement for getting the input, otherwise you directly pass the values to through the function to calculate. Okay. So here I have launched the kernel at triple angle bracket open 1 comma 1 and triple angle bracket close. So I am having values of A, value of A is 2 and value of B is 7. So next, I have one variable DC. So here I am using the variable C for storing the results by adding A and B. Okay. So that's only I am using the variable. All the values of A and B are immediate values. That's given 2 comma 7. Okay. So next, what happens here is directly the CPU directly transfer this data to GPU while launching this particular kernel, and it says it has to store the results to DC. Okay, so there is no need to explicitly write code for that. You can simply launch the kernel. So what next we have to do is 2 plus 7 is done there in the GPU. Okay, the result is stored in DRAM of GPU. From there, we have to copy that particular result onto CPU. Okay. For that, we have to use one more statement, CUDA mem copy, MEMCPY. Okay, this particular statement is used for both copying data from CPU to GPU and GPU to CPU. Here, we are using it for copying data from GPU to CPU. Okay. So here in CPU, the corresponding variable for DC is C. So you give ampersand C, comma DC, size of int. The size for our variable is integer. And this particular statement is important. CUDA memcopy device to host. Okay. So you copy the data from GPU to CPU. Okay. So in GPU, we are having the variable DC and CPU you are having the variable C. Okay, from DC the data is transferred to C in CPU. Okay, so now it has reached there in CPU. After that, you can easily print the value on the screen. Okay, so any doubt in this particular program? So here you don't need of any device synchronize. Okay, CUDA device synchronize is not needed. I'll tell the reason later. Oh, I have pasted the program. Okay, okay. Uh, so some people have executed the previous one. Very good. So I have pasted this program in the chat box. Okay, you can execute. At the same time, I do executing. So at last I will share the notebook too. You have to give the file name, copy and paste. Add one.cu. That is the file name. All the other things I have pasted. Okay. So next, I have to compile. Okay, I have compiled here. Okay. So 2 plus 7 is executed and the result is printed. Okay. For all the statements. Okay, so here you can do one change here. So instead of directly giving 2 comma 7, so you can declare variables for 2 and 7. So you can, of course, you can give in a comma b comma c. So also if you have allocated 3 variables there in CPU, you have to allocate 3 variables in GPU too. Okay, and after that uh, you have to write CUDA malloc. Okay, for allocating memory space there in the GPU. After that, you use scanf statement for getting values for A and B. Okay, in Colab too, you can do. And after that, you can simply launch the kernel with the help of the statements. So here you give, instead of 2, what you have to do? You can give, for example, if you have given DA, DB, you can directly give DA, DB and DC. So once the calculation is completed there in GPU, so while launching kernel, what happens? Directly it calls this function. Okay, this function says C equal to A plus B. Automatically it will be added, and that is stored in DRAM of GPU. Then you can copy the result to CPU, then you can print. You can do the change and you can try to execute that program. Anybody wants to try it now? You can try. Okay, some small variation I have done it here. You can see this one. Okay, so here what I have done is the some extension of the previous one. So here I have declared three variables in CPU A, B, and C, and also I have declared three variables for GPU device A, device B, device C, and so you know how to calculate the size of integer. Then I allocating device copies of ABC. So you have to allocate three spaces there in GPU. So use that CUDA malloc. So for variable A, B, and C. Okay. So if you don't want to give size here, you can directly give size of int here itself. No problem. So here I have assigned the values A equal to 2, B equal to 7. Okay. And what else you have to do is you have to copy the data A and B from CPU to GPU. Okay. So in the previous program, the kernel itself, I directly pass the values. Okay. So here I am assigning 2 to A and 7 to B. The values are there in variables A and B. Okay. So you have to copy both the values A and B from CPU to GPU. CUDA memcopy DVA. This is a corresponding variable for A, ampersand A, size, CUDA memcopy host to device. Okay, you can see the difference. Here it is copy from device to host, CUDA memcopy device to host for result. For copying from host to device, here you have to give the CUDA memcopy host to device. Okay, so you can give it a single statement because of this box. It comes to two space. Okay, it's not a problem. And the second one for variable B, again you have to give CUDA memcopy. So dev B ampersand B size CUDA memcopy host to device. Okay, both the values A and B is transferred to where? GPU. Then you launch the kernel and while passing the parameters, what are the parameters you are having? Having the variable A, B, and the result has to be stored on C. Okay. So now what happens? This kernel function is called and A plus B is calculated and the result is stored in C. In here it is stored in dev underscore C. So again, like previous program, what you have to do is you have to copy it from device to host. Then you can simply print. So once it is completed, okay, so after printing the result, okay, what you can do is you can simply free the memory which we have already allocated in the GPU. That has done with the help of CUDA free. Okay. So here I have to paste it here, no? It will be pasted as two messages. So we can't directly paste it from device. Okay. So the data has to be moved from CPU to GPU. After that, GPU to CPU, then only you can able to paste. Otherwise, we couldn't get the data from GPU. Okay. So I have pasted the program there. So what are the changes you need? You can do some changes. Okay, like giving scanf statements, like, and you execute the program. So any doubt in this last one? Yeah. So in the last class itself, we have discussed there are some latencies there while transferring data from CPU to GPU and GPU to CPU, but throughput is high while comparing CPUs for any computations. Okay. For getting high throughputs, so we can go for GPU. Okay. So the latency for data transfer is not at all considered. So while executing therein CPU and GPU for the same task, okay, the throughput is very high there in GPU. So have you executed this program? Oh, I have this program here. So I have given some other variables. Okay. So here I have given two values 3 and 5. Okay. So the result I have got is percentage D. So we'll discuss CUDA error, everything in the next class. There are some other statements are available. Okay. So actually, in memory management, what you have to remember is, so already we have seen in the architecture diagram of GPU and CPU and all. So there is no main memory in GPU, and the device memory for host and device memory are different entities. There are so many similarities there. But instead of installing all the CUDA drivers and API, everything, so the CPU can directly contact with the GPU memory. Okay. So that's why we are transferring data from host to device and device to host. And device pointers point to GPU memory and maybe pass to and from host code, may not be dereferenced from host code. Host pointer point to CPU memory, that is CPU, maybe pass to and from device code, may not be dereferenced from device code. And here there are some CUDA API for dealing with device memory. Already we have seen that CUDA malloc, CUDA free, CUDA memcopy. And these are all C equivalents of malloc, free, and memcopy. Okay. So these are all some of the references. I have taken some of the things from these textbooks. And say any other doubts? I do. Have you executed the last program? Anyone? Okay. Okay. Thank you. So thank you all. If you are having any doubt, don't hesitate to ask me. If I am knowing anything, I will share with you. Okay. Thank you once again. We'll see you tomorrow at the same time.